Hello, ETHDenver. Welcome to the second half of the Besu hour over here at the Captain Ethereum stage. My name is Gary Schulte. I'm a blockchain engineer with Consensus. I've been working on Besu since 2021. My talk is on EVM transaction parallelization, not on layer 2, not on a special blockchain. We're talking about layer 1 transaction parallelization today. It's a deep topic, but it's fairly accessible. In the interest of time, though, I'm just going to get on with it. So Ethereum is scaling. Layer 1 scaling. Layer 2 is scaling. We're seeing asks for more block gas. There's new cryptographic primitives coming online with PeerDOS, with Verkle, pretty soon now with Pectra. The TLDR here is that we're asking more and more out of our execution clients, and they need to get things done as quickly and efficiently as possible. So, as I said, my talk is on execution specifically. In any 12-second Ethereum slot, 4 of those seconds are dedicated to block execution. If we can use as little as possible of those 4 seconds, we can yield that time back to our consensus client. We get better attestation times, we get more time to propagate, we get better financial performance. The network is happier overall. Everybody's happy when we can execute as quickly as possible. So if we want to eat as little into that 4-second window as possible, what are we typically doing during those 4 seconds? There's a couple of things that take most of the time. The first is we're executing transactions in the EVM. I mean, fundamentally, that's what's going on when we execute a block. The next thing that we're doing that takes time is we take the results of those transactions and we apply them to state, and we calculate a root hash, and we do all of that work. This talk is focusing on the former, just the transaction execution, and specifically doing that in parallel on multiple cores so that we can get that done as quickly as possible. So, a quick history lesson. Ethereum pre-Byzantium. What does pre-Byzantium Ethereum have to say about transaction execution? Well, the white paper specifies that we have a shared global state, and transactions should be executed against that shared global state in the order that they were packed into the block. That ensures that all the different clients arrive at the same answer, have the same end state, by executing the transactions serially. Originally, there was actually a kind of hard requirement to execute transactions serially. The transaction receipt for each transaction needed to include an intermediate state root. That means that you execute the transaction, you apply the results of that transaction to state, you recalculate your state root, and you include that new intermediate state root along with the transaction receipt. And you do this for every transaction until you get to the end of the block. As you can imagine, that's not as efficient as it could be. That creates write amplification, and it just makes things run a bit slower than needed. So in Byzantium, EIP 98 and 658 relaxed that requirement so that we don't have to include intermediate state roots. We just instead include a Boolean to say, yes, the transaction action succeeded or the transaction failed. Now that was a good unlock in terms of being able to aggregate the results of all of these transactions and applying all of that state change at the same time. We get rid of that write amplification, and everything when you do it in batch is faster. So that was a good unlock. But in terms of how that applies to parallel execution, now that we don't have to calculate that intermediate state root, we can execute the transactions in any order we want and in parallel. The only thing that we have to worry about is when these transactions are touching or mutating the same shared global state. So with that in mind, what kind of parallel execution strategies might you implement in order to be able to leverage multiple cores? Well, the simplest strategy is just don't parallelize. You know it's safe. You know that it's protocol specified. You know you're going to get the right result. Incidentally, you're also going to end up with the worst case block execution. And that sounds bad, but it's actually useful because we don't have any guarantee about a rate of conflict in any particular block. We don't have any guarantees about what performance we're going to gain from executing things in parallel, because it's kind of trivial to create a block that has 100% conflict. So when we're setting gas targets, when we're trying to think about our worst case, we need to consider all the transactions executing serially. So that strategy is probably not going away anytime soon, if only because it informs our worst case. So if you do, though, want to take advantage of multiple cores and try to get execution running faster, some strategies you might think to implement would be like pessimistic lock-based synchronization. There's been some presentations here, I think Arcology, maybe Aptos. They're talking about locking state, moving state, all these things that allow you to do some intelligent scheduling of transactions that might otherwise conflict. The Ethereum protocol, the core L1, layer 1 protocol, it doesn't have those primitives. It's just a non-starter. So that leaves us really with just optimistic execution. Optimistic execution would just see us execute all the transactions in parallel against our shared state and try to detect and handle these conflicts. So what strategies, what optimistic execution strategies might work? One is somewhat naive, and that is to just assume everything's in conflict. You run all your transactions against your shared state, and you just presume that everything's in conflict, and you throw all the results away and re-execute that block again serially. And it might seem kind of strange, like why would you bother to execute something in parallel just to re-execute it again serially? Well, there's some benefits you can gain there. One is that when you're executing transactions in parallel, you're able to load everything from state that you need in order to execute your transactions. And any expensive compute operations, you can cache those and hang on to them, so that when you get rid of your parallel results and you re-execute in a serial fashion, there's minimal I/O weight, there's minimal CPU weight. You're running that block in serial as fast as is possible. Incidentally, this is the basis for Nethermind's pre-warming feature. Nethermind implements a Ketchak hash cache, where they keep all of the recent results of hashing values, and a precompile cache, where expensive precompile computations are cached, and also a storage cache, so that when Nethermind re-executes its block in serial, it's got all the advantages of everything sitting there waiting for it. Another strategy might be to try to detect and handle these conflicts. Instead of throwing away the results, you somehow try to detect in what way they're conflicted and resolve that conflict. So like the prior strategy, you would execute everything in parallel against your head world state, and then you would try to aggregate all of those results in the order that the transactions were packed into the block. At the time that you do that aggregation, that's where you do your conflict detection, and when you find conflicts, you re-execute against a state that has already had its prior transactions merged into it. The core of this strategy, what makes it possible, is that conflict detection. And this is the strategy that Besu implements. And I work on Besu, so I'm going to talk about it. So a quick recap on Bonsai. Bonsai is a storage format, the default storage format for Besu. Where Bonsai is relevant to parallel transaction processing is in that it provides a few key features that allow us to do this. Bonsai provides a single semantic worldview. There's only a single state tree, a single flat database stored on disk at any time. That's how we save on storage. We have a small storage footprint. That's kind of the primary value that Bonsai has been bringing. But also, any diff to that world state, any prior block, any future block, or whatever, is stored as a diff to that state. So you can think of a Bonsai world state as like a Git repository that you can roll back and forth to any particular commit. So one of the features that make parallel execution possible is in-memory world state overlays. Bonsai, what it does is it provides an in-memory overlay for that semantic world state so that you can read it, you can write it, you can mutate it, you can roll it back and forth, and you can persist it to disk as a diff. But what's great about that is that you can also clone it. You can create 20 copies of the head world state. You can create 100 copies of the world state. You can create 1,000 copies of the head world state. And it's just a map in memory that is an overlay on top of it. This is how we can duplicate this head world state and allow all of our transactions to run in parallel against their own segregated, I guess, world state. The next feature that Bonsai gives us that makes this possible is the accumulator. The accumulator data structure is specific to any particular world state. Every world state has its own accumulator. And the accumulator is tracking any reads or any writes or any updates to that world state. So that gives us kind of a summary of what happened when we execute a transaction against this isolated world state. It lets us know anything that happened, anything that we touched, read, write, or mutated during that block, during that transaction specifically. So this is the basis for our conflict detection, that accumulator data structure. So Besu is using Bonsai as a type of software transactional memory. Software transactional memory is a class of concurrency control that allows you to do optimistic parallel execution against shared memory. In this case, that shared memory is our head world state. And we take multiple copies of this head world state, as I said before, and we give each transaction its own private copy, and we kick off all of those transactions in parallel against all of the cores that we have available to us. Once all of those transactions are complete, their accumulator has the summary of all the changes, all the touches, all the mutates, and we can merge them into a single world state, a single intermediate world state. And as we merge those, we check for conflict using the accumulator. So for example, transaction 1 completes, we merge its accumulator into our intermediate state, and that's fine. There's nothing it can conflict with. It's the first transaction. The second transaction, we merge its accumulator in, and the first thing we do is we say, has anything in here been modified in this intermediate state? If it is, we kick it out, say, this has a conflict. We need to re-execute this against this intermediate state. And if not, we just merge it. So we do this for all of the accumulators, and at the end of that block, we have a resulting world state that has been parallel executed, or at least as much as possible has been parallel executed. So this is all core depending on detecting conflict. And detecting conflict has a couple of properties it needs to do. It needs to be fast, and it needs to be correct. It's kind of pointless if you parallel execute a block and the conflict detection algorithm is so expensive that it's more expensive to run a block in parallel than it is to run that block serially. So what we've done is we've ordered these checks to be as cheap as possible and the cheapest first. We want to fail fast so we don't waste time with expensive checks. The first thing that we're doing is account level checks. If an account that's modified or touched by a transaction has a nonce or a balance or a code hash or whatever that's already been changed in the intermediate world state we're trying to merge into, we mark it for conflict. If not, we move on to contract storage. If a transaction modifies contract storage, transactions can modify a lot of contract storage. There's several things in contract storage we might need to, in elements you might think, that we could potentially change. So we save this check for the last because it's just a more expensive check to make. We look at all of the elements in contract storage that have been either read or updated by this transaction, and we make sure that they haven't been modified already in that intermediate world state. If it has, it's conflicted, check it out, re-execute. If not, we merge that in. We do this for all of the transactions in the block, and the resulting world state has all of the changes from all of the transactions. Now we take all of those changes and we merge them into the state tree. and then we recalculate the state root, and we take that state root and compare it to the state root that was advertised in the block header. If it matches, we're good. We just parallel executed a block. If it doesn't match, something went wrong. Either that block was invalid to begin with, or that something happened during the parallelization, a race condition, or maybe a false negative for conflict detection. So in Besu, we add a fallback to serial execution. If we detect a state root mismatch, we want to be certain that it really is a bad block before we report to the consensus layer that it is a bad block. Not to put too fine a point on it, how well do Ethereum blocks even parallelize? If we try to run things in parallel, what might we actually see? There's a couple of things that play into that. Each block is different, as I mentioned before. There's no guaranteed rate of conflict or parallelism. So the contents of the block kind of define this high watermark of what might be parallel. Then it comes to the hardware itself. Since we're using multiple cores, we're running all of these things in parallel. We're trying to get all of these parallel transactions completed in time to merge them into the block at the time we're trying to do block processing. So if those parallel transactions haven't finished, maybe the hardware's under-provisioned, maybe it's like a 2017 era NUC or something like that, it just doesn't have the horsepower to get there in time. In that case, we, at merge time, run that transaction in serial. So if you look at the chart here, this is a sample. This is, this is my own personal NUC. It's the Solo Staker Special, just an Intel processor, like a $600 computer. And you can see that on Besu, on that type of hardware, on commodity hardware, we're achieving moving average roughly 60 to 65% of our transactions on mainnet are successfully running in parallel. We're considering that a pretty good result. The RETH team did an analysis of historical Ethereum transactions, and they determined that roughly maybe 80% of transactions might be parallelizable. So when we're in real time getting 60 to 65%, we're pretty happy with that. So what's the net performance? On that same NUC, we're seeing, for that 24-hour period, on average 160 to 170 mega gas per second. That's 160 to 170 million gas per second. Again, this is block subjective. Blocks that are full achieve a higher throughput than blocks that are empty. Not all operations cost the same. And again, it comes to hardware. So, whoops, I missed a slide. What are our recommendations? The takeaway should be that parallelization isn't a slam dunk. You don't always want to enable it because it is hardware dependent and it is block dependent and use case dependent. So conflict detection itself is a cost. It's strictly a cost. And the heap memory pressure from these additional world states that we're using for parallel transactions, that is a cost. The resource consumption using all these extra cores, that might cause some contention for inter or intra processes. You might see some things shift around. The takeaway is, the TLDR is, if you are interested in high performance execution, if you want good validator performance, if you're running on an L2 using Besu as your execution client, you should seriously consider enabling this feature. We're finding the best trade-off is right around 8 cores, maybe 4 cores if you've got hyper-threading and you've got logically 8 cores on a 4-core machine. That's pretty good. We recommend going that route. We want you to try it out. That's what we're trying to get here today. Besu has had this feature since 24.7.1. It's been marked as experimental while we iterate on conflict detection and as we improve the conflict detection to reduce our false positives. The Besu 25.3 release is going to have the best of breed of this probably final form of conflict detection. So we want to get that out there and get people using it and testing it. And if you want to try it out on your own Besu node, it's still marked as experimental, but probably soon going GA. That is the long and the short of it. Give it a try. I've got questions, comments, or feedback. Let me know. You can hop into the Besu mainnet Discord on the Consensus Discord or the Besu channel on LFDT. Thanks very much.